How's it going, guys? We're back with another lecture, this time on spanning sets. This lecture is going to be predominantly definition-based. I need you guys to know what a spanning set is and perhaps be able to identify when you have a collection of vectors what it spans. Okay, so there's not a lot of prerequisites here, just vector space terminology so that you guys are aware of some of the vocabulary I'm going to be using. Okay, let's go ahead and get started. The first thing I have to do, unfortunately, is give you some more vocabulary. So I need to define a few things for you. I need to define a linear combination of vectors. So a linear combination of vectors. Okay, and we'll take a collection, just arbitrary v1, v2, all the way up to, let's say, vn. Okay, these are n vectors that we have. Okay, and again, I'm not putting the little arrows on top of these. They might be vectors in the sense that they might be, you know, like the arrow vectors, but they may not be. When I say vector here, I just mean some element within a vector space, and not all of those are. Not all of those are again the little arrows. So if I want a linear combination, what I'm going to do is I'm just going to take multiple copies of these things and add them together. Formally defined, a linear combination of vectors is some constant c1 times vector v1 plus some constant c2 times v2, etc., plus some constant cn times vn. So again, this is just a sum of, let's say you've got 3 times vector v1 plus -5 times vector v2, blah, 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 plus maybe 1/2 times vector vn. So for some scalars, Cn are scalars. For some scalars, C1 to Cn. Okay. Okay, fine. Again, so if I have, just as an example, if I have, let's say, the vector 1, 2, and the vector -2, 3, okay, then this is a linear combination. Let's say, I don't know, 4 times 1, 2 plus -2 times -2, 3. Right? So this is a linear combination of these vectors. Okay, now, if I look at a collection of vectors, well, I might ask myself, okay, well, what are all the things I could possibly make using those vectors? Okay, the example I just had up here, I kind of wish I hadn't erased it. Okay, but let's say, again, what was it? It was 1, 2, and -2, 3. And even if it wasn't, we'll just use this as a new example. Again, we said that, let's say this was a linear combination, 4 times 1, 2, plus -2 times -2, 3. And if I actually work this out, of course this comes out to another two-dimensional vector here. This comes out to be 8, 2. Right? Again, when you add vectors, you'll add them component-wise, so you'll distribute, and then you'll add component-wise. So what we say then, we say that 8, 2, the vector 8, 2, is in the span of these two vectors. Okay? The span, or the spanning of, okay, the span of these vectors is the collection of all the vectors that you could possibly build using linear combinations of them. Okay? Now this is going to be very important for us because we're going to use this to be able to write the solutions to some of our differential equations. Our differential equations are not going to have singular answers, or at least even finitely many answers. We're going to have infinitely many answers to our differential equations, and we need an efficient way to write them, and so we use spanning sets, right? I don't need to write all infinitely many solutions if I can come up with a collection of vectors whose span is all of those solutions. Okay? All right, fair enough. Let's get some examples up here, just because this is somewhat easier if you play around with it. Just so that you guys have something to follow along with, I'm going to use the examples out of your book. I might throw in maybe one or two more, that aren't in there, but I'll do a couple of the examples out of your book so that you can follow along in text just in case, but just to flesh these out. Okay. So the first sort of exercise we have is that let's show that R2 is spanned by, and we just have a couple vectors here. I'm just going to use the same two that I was using. There we go. Let's show that R2 is spanned by these two. So what would this mean to say that R2 is spanned by this? So what this statement is trying to say is it's trying to say that any vector you choose in R2, any at all, it can be written like this, right? So it's trying to, here, let me get another color. So this is trying to say, choose some vector V, which is a member of R2, then there are C1 and C2 such that V is equal to C1 times 1 comma 2 plus C2 times negative 2 comma 3. Okay? Now, again, it's important that when I say choose, I mean this is the arbitrary choice. You don't actually get to choose one. If I want to show this is true, okay, then I want to show that this is true without actually picking a vector. If I pick, like, let's say 1, 5, and I want to show that 1, 5, so what I do is I find C1 and C2 such that these things add up to be the vector 1, 5. That doesn't help me, okay? That's a fantastic way to show that 1, 5 is in the span, not that every vector in R2 is in the span, okay? So how would we do this? Well, I mean, it's pretty easy. Let's say V is equal to A comma B, okay? Then I can set A comma B equal to C1 times 1, 2 plus C2 times negative 2, 3. Well, again, I can still distribute and expand these things. So I have A comma B is equal to, if I distribute C1, that gives me C1 comma 2C1. And I distribute C2, I get negative 2C2 comma 3C2. And now we add the vectors component-wise. And so I get a vector on the right-hand side whose first component is C1 minus 2C2, and whose second component is 2C1 plus 3C2. Now, how does this help? Well, you'll notice that this actually provides me with a system, because again, these components don't interact. The first and the second components don't. What this actually gives me is that I know for this to work, I know that A has got to be equal to C1 minus 2C2, and B has got to be equal to 2C1 plus 3C2. Okay, again, first component must be equal to first component, second equal to second. Now, let's, again, I'm looking to verify that for any given A and B, right? Any vector here, any given A and B, that there are in fact solutions to this. Well, how do I verify that? Well, it's pretty easy actually, right? This is a linear system. If this representative matrix has rank 2, won't this system have a unique solution for every possible choice of A and B? That's part of our invertible matrix theorem, right? Yeah? I know that this representative matrix, let's call it A. So A is equal to 1, -2, 2, 3, right? I know that A times this C vector, so A times C1, C2, is equal to this vector V, that this has a unique solution, therefore has a solution, as long as A is invertible. So as long as the rank of A is n. Well, it's pretty easy for us to verify that the rank of this is 2, isn't it? Right? I suppose we should do that for completion's sake. But taking A and applying just one elementary row operation, namely A12 -2, okay, leaves me with 1 -2. This will be 0. This will be 7. And we see that this is going to be a rank 2 matrix. If I multiply the second row times 1/7, that gives me my row echelon form. So this is rank 2. Okay? This is rank 2. Now, it's important to understand, I didn't actually find C1 and C2. I can't, right? I'm trying to prove that they exist for all possible vectors that you could choose, which means I can't come up with explicit values for C1 and C2. I mean, I could given any given vector just by solving this, but I've shown that every possible vector that you could give me, every V, right, every vector V, which is AB, okay, has a solution. It has a C1 and a C2 where you can create this vector. These are all the vectors in R2, okay? So yeah, R2 is spanned by these two matrices. Now to be fair, this is a very complicated spanning set. So we call a collection of vectors which spans a space a spanning set. This is a very complicated spanning set for R2. We have another spanning set. This one is sometimes called the canonical spanning set, and it's present for every vector space that you could have. R2 is also spanned by this set. 1, 0, and 0, 1. This one's easy, right? If you give me any arbitrary vector AB, I know that it's A times 1, 0 plus B times 0, 1. This one kind of feels like cheating, doesn't it? Okay? The word canonical means just sort of most naturally arrived at. And so this canonical basis, or canonical spanning set, we can come up with one of these for any given vector space. And I'll work through a few of them right now just because. So if I wanted let's say a spanning set for P2. Let's see if we remember what P2 is. P2 is the collection of polynomials of the form ax squared plus bx plus c, where a, b, and c are real numbers, right? So it's quadratic sum below, right? Because a could be 0, b could be 0. Now, what's my spanning set? Well, okay. What if I just look at my independent choices, A, B, and C. What if I just let one of them be 1 and the rest of them be 0, and I alternate that, right? So what if I make my three vectors? V1, let's make that 1x squared plus 0x plus 0. Let's make V2 0x squared plus 1x plus 0. And let's make V3 0x squared plus 0x plus 1. So you see I just rotate which of these free choices I get is a 1 and which ones are zeros. Now this, of course, we can clean this up a bit, but what it gives me three functions, right? It gives me x squared, x, and 1. And so if you're looking for a spanning set, x squared, x, and 1, the span of this is P2. Okay? So this is a spanning set for P2. Everything in P2 can be made by taking a linear combination of these, obviously, because that's how it's written, right? I maybe do one more, just because it leads into the next example I'd like to do. Okay. How about for M2? M2R. Okay, so how about for M2? So M2R, what is this? This is the collection of 2 by 2 matrices such that every element in those matrices are real numbers, right? Okay, fine. Let's think about what it looks like. An arbitrary matrix from this set looks like this, right? A, B, C, D. It's just 4 entries, right? It's 2 by 2. And I can make a spanning set by doing the same thing, right? I've got 4 free choices. I'm going to let each one be 1 and the rest of them be 0 alternating. So that's going to give me, okay, my first element's going to be 1, 0, 0, 0, right? And my second one, 0, 1, 0, 0. And my next one, 0, 0, 1, 0. And my last one, 0, 0, 0, 1. Yeah? So this set spans M2R. Okay? It's a spanning set for M2R. Okay? Not terrible. Coming up with canonical bases are not awful. Okay? But this is a useful construction that we will use periodically. Okay. Let me work another example. The next example I want to work uses M2, which is why I did that one. Okay. So let's see. This one says verify. There's a lot of math words for prove this, right? Yeah, verify, show, demonstrate. Okay. Verify that A1 is a matrix, which is 1, 0, 0, 0. A2, that's 1, 1, 0, 0. A3, which I'm pretty sure is 1, 1, 1, 0. Let me make sure. Yes. And A4, which is 1, 1, 1, 1. Verify that these span M2. Okay? Now, these are not the canonical bases, right? But, should be fine. Let's do the same thing we did before, right? If I claim they span M2, I'm claiming that every matrix in M2 can be written as C1 times A1 plus C2 times A2 plus C3 times A3 plus C4 times A4. Okay? Every matrix. Okay? I'm going to call this matrix, again, I'm going to pick something arbitrary here. B1, B2, B3, B4. Call this matrix B, and there's matrix B. But if we look at what this sum actually represents, look at the 1, 1 entry, right? Again, when I multiply C1 times A, all I'm going to get is a matrix that reads C1, 0, 0, 0, right? Here for C2 times A2, I'm going to get C2, C2, 0, 0, right? So if you just look at the 1, 1 entry, on the right-hand side, the 1, 1 entry is B1. On the left-hand side, it's C1 plus C2 plus C3 plus C4. Those are all the 1, 1 entries from this linear combination. Okay? Second, look at the 1, 2 entry. On the right-hand side, you've got B2. On the left-hand side, you just have C2 plus C3 plus C4. If you look at the 2, 1 entry, you've got B3 here. Here you've got C3 plus C4. And then if you look at the 2, 2 entry, on the right-hand side, you've got B4. And then you just have C4. Well, okay. Does this always have a solution, right? That's what we're looking for, okay? We want to make sure that there's no matrix here, there's no collection B1, B2, B3, B4 that I can't create with these arbitrary coefficients. And it turns out, no, we can figure this out by some back substitution, okay? If you give me B1, B2, B3, B4, I know that I can just set C4 equal to B4. And then substituting that back in, I can set C3 equal to B3 minus B4. Again, if C4 is equal to B4, then you can subtract that over, right? And of course then, fine, that would make C2 equal to, again, we'll do our substitutions here. This will be C3, we know is B3 minus B4. C4 is just B4, so C2 is just B2 minus B3. The B4 and the negative B4 will cancel. Okay? And what about C1? Okay. Well, again, substituting these back in. C2 is B2 minus B3. C3 is B3 minus B4. C4 is B4. C1 is just B1 minus B2. And so if you give me any matrix you want, right? Any matrix you want, let's do an example. Okay, so for example, let's say you want to know if 7, 3, 1, negative 5 is in the span. Well, these rules give that to you, right? They say let C4 equal negative 5, let C3 equal 6, so B3 minus B4, so 1 minus negative 5. Let C2 equal 2, 3 minus 1, and C1 equal 4. Okay? Again, B1 minus B2. And if I set these coefficients here, the sum I get is 7, 3, 1, negative 5. Okay? Now remember, again, we don't have to find, this is just an example to show you that this works. We don't have to find a specific example here, okay? We're looking to show that it works all the time. All I've done here is I've demonstrated that you can find coefficients, okay? I don't actually have to find the coefficients because I would have to do that infinitely many times. I'd have to do it once for every vector in our, well, here in M2. And there are uncountably infinitely many of those, so that literally can't be done. Okay. All right, guys. So I want to cover just a couple little technical things here. I'm not going to go through the proofs, but I do want to sort of go through these, and I might just talk about them a little bit. So a few notes on spanning the spans of vectors from a vector space. Okay. This seems a bit trivial, but we'll go ahead and make the definition here. What would the span of the empty set be? So I don't have any vectors to work with, right? So how do I make a linear combination if I don't have any vectors to work with? Well, we defined this as the zero vector. Again, zero vector, not the number zero, okay? We just defined the span of the empty set to be the zero vector for whatever space you're working in. There are reasons for it. I'm not going to get into them, but this just sort of makes everything run a little bit nicer, a little bit smoother. It takes out some of the trivial counter cases for some things, okay? But more importantly, this statement's a little bit more important. Okay, so here's one. Two, given some collection of vectors taken from a vector space, again, this is just some collection of vectors, don't know what it is, okay? Then the span of that collection is always a vector subspace of the parent space. Now remember what we were saying in 4.3, we were talking about subspaces. We were trying to prove that some subsets were in fact subspaces of vector spaces. Just because it's a subset, the span of this would have to be a subset. Just because it's a subset doesn't mean it's a subspace. The subspace has to maintain those same 10 vector space properties. 7 of them, of course, are inherited, but we had to prove for the other 3 the existence of zero, closure of scalar multiplication, and closure of addition. Well, yeah, but the span of this is a linear combination, which we make by scalar multiplication and addition. So, trivially, this thing, because it's a span, satisfies those missing properties. And so everything you make like this is already a vector subspace. That's very nice for us. Okay? We're going to use this fact to be able to clarify, or at least be able to describe some of the infinite solution sets that we're going to work with this semester. Okay? All right. This is going to make a bit more sense, and you'll get used to writing things this way once you do just a few of the homework problems from section 4.4. As usual, those are already listed for you on Canvas. So if you have any questions, again, shoot me an email. Bye.